So yesterday I was taking a look at what we've been doing the entire unit, and I came up with a couple of notes. There are 4 things that I realized that we do for every single problem. It doesn't matter what the problem is, if it's just a horizontal motion, if it was like our elevator problems from last night, which we will take a look at some of those, or if it's like the 2 new problems that we're going to be taking a look at today. It doesn't really matter, those cases. We still do these 4 things, and I know it's a little light because I have the lights on. But the first one says, draw the free body diagram of the situation and make sure that all of the forces are in the X or Y direction. Right? So we have to make sure all of them. We're going to learn something new today where we see a situation where the force is not necessarily in the X and Y direction, and we'll have to break it apart. Number 2 is still ID the unknown. That's the U in PUCM. And so that's nothing new. Step 3 is to set up your knowns chart. We actually have 2 different kinds of knowns charts. We can have a kinematics one that had V naught, V, X, A, and T. Or we can have the forces one that has A, M, and then the sum of all of your forces in the X, Y direction. And the last one, number 4, says set up your F-net equations and solve. And one of the strategies that we've been learning this entire time is that if you're missing acceleration and you need it to solve the problem, try finding it using kinematics instead, right? Try finding it using kinematics, because you could use the A in V naught, V, X, A, and T in order to solve for your force ones. Or vice versa also works. If you're trying to solve for kinematics, you don't have your acceleration, use your force. And we're going to see that in our very first example. So, for new material, and please continue to take notes, we're going to take a look at a situation that is in our packet. It's on page 18. And if you take a look at the bottom of 18, it says component problems. Would someone read that problem to me, please? And give me a second to find my other marker. Here it is. Where it says component problem, and it starts with a boy pulls upwards.
Boy pulls upwards at an angle of 20 degrees with a horizontal force of 10 newtons and a 7 kilogram wagon. If the force of friction is 3 newtons and the wagon starts from rest, how long would it take to move the wagon 15 meters and determine the normal force acting on the wagon?
Okay, you gave me a lot of information, but step 1 was to do the free body diagram. The free body diagram that I have up on the board, yeah, that works. The one that I have up on the board shows that we have a force of friction, a normal force, this applied force of 10 newtons, and a force of gravity. So I have all of the forces listed there. You also gave me information about kinematic stuff, which is good considering that my unknown, it says how long did it take to actually travel 15 meters. So we don't even have to worry about forces right now. What we need to do is take a look at kinematics. So my kinematics XY chart will look something like this. They told me that it was going to start from rest. They told me that my displacement is going to be 15 meters. Shoot. That's it. That's all I know, right? So,
The acceleration in the Y, you made them that way.
in this case, we are dragging an object on the ground, so the acceleration in the Y wouldn't be negative 9.8 because it's moving only horizontally.
Okay.
It's not freely falling. But I don't have enough to actually solve. So what is one strategy that we know? Maddie?
You make the other chart, like with the AM and the forces, and then you solve for acceleration and put that in the kinematics one.
You trailed off there, but you're absolutely right. It looks like if I'm able to solve for the acceleration in the X here using my forces, I could use that information here, and then I would have 3 things to solve for the time. A great strategy. Now, in order to fill this in, we don't know what the acceleration in the X is. That's cool, but the mass, that was 7 kilograms. And then it says the sum of all of the forces in the X. I have one. I'm going to pick the easy one. That's the negative force of friction. Are there any other forces in the X? Paula?
Oh, the 20-degree one with the
Yeah,
10.
this one's kinda in the X, right? It kind of goes in the X direction, but it also kind of goes in the Y.
So you find the vector, the horizontal vector.
Wonderful. If I were to split this up, because the 10 Newton force does not go just in the X or just in the Y, I can't place it on this chart. So one thing I could do is I could break this up in terms of the vector components. And so I could go 10 times the cosine of 20 degrees, and I think that turns out to be 9.4 newtons. And then this one I could have 10 times the sine of 20 degrees, and that turns out to be 3.42 newtons. Just kind of guessing on those ones. But now that I have that, I know that there is an applied force in the X direction. If I wanted to see the forces in the Y direction as well, because we will need that for the second part, my acceleration in the Y, as you pointed out, Avery, is 0. My mass in the Y is still 7 kilograms, because that's a scalar. But I do have two forces in the Y, Fg and Fn, right?
And then you have the applied force.
Totally, I was just getting there. I have a negative F of G, a positive F of N, and I'm running out of space here. I also have a positive applied force in the Y. You guys all see that? I don't just have these two, I have this one as well. Okay? And we'll get there in just a moment when we have to solve for the normal force. But right now, my goal is to solve for the time. I can't solve for the time without the acceleration, so I need to solve for the acceleration. But you can see that I was given my friction, which was negative 3 newtons, and I calculated my FAX of 9.4. That was a positive 9.4 because it was directed to the right. So I have the sum of all of my forces in the X. And that should equal the product of A and M. And so now that's the only thing that's missing out of this whole equation. I now can solve for the acceleration and put it right here, acceleration in the X. And I will have that value in order to solve my kinematic equation. Delta X is equal to V naught T plus 1/2 AT squared. You guys all see that?